Okay, so in this lesson we're going to look at the modulus in functions. We've already looked at modulus in part, but we're going to introduce some modulus notation with our function notation and consider what that's going to do to affect functions in terms of what their graphs look like in particular. And we're also going to look at combining functions too. So here's your starter. I'd like you to just have a look at that very first example. We've got a of x, which we're told is x plus 1. And then in the first row of this table, we've got b of x, which we're told is 2x minus 1. And then if you look at the first column, that first column is ax plus bx. So two functions added together. Now, can you figure out why we, as a result, get the graph of y equals 3x when we plot ax plus bx? Hopefully you can. So what I'd like you to do is to have a go now at the completing sketches for those remaining 5 boxes. Sketching what you think ax plus bx, ax minus bx and ax times bx would be for the first row where bx is 2x minus 1 and the second row where the bx function has been changed to x squared minus 5x plus 8. Pause this video now, and when you've done, click play to see if your answers were right. So well done if you managed to get these answers here. This is effectively combining transformations. Now don't worry too much if you struggled on this, particularly towards the end. And if you want more detail, there's actually a link at the top of this screen here which talks through a few of these solutions, which you might want to have a look through, particularly if you're still a bit unsure of where you went wrong by the end of today's lesson. A PowerPoint's also been attached with today's lesson, so that's also available to you. Follow that link. Okay, so sketching y is equal to the modulus of a function and sketching y is equal to a function of a modulus of x. What is the effect of those two going to be? Now, I would say, on first impression, it might be that those two are equivalent to one another, but thinking carefully about what the modulus does tells us that that's not the case. Now we know that the modulus of a function always tells us the scalar value, the size of that value. It's always going to be positive. So if I consider a function y is equal to f of x, and it looks like this particular quadratic here, we can see it intercepts the x-axis at 3 and negative 1 and the y-axis at negative 3. Now I know if I take the modulus of that entire function, it is never going to be negative. The smallest value can never be is 0. And so I'm going to find, if I sketch this function, that the negative component of it gets reflected in the x-axis, and we end up with this sort of a shape here. So let's have a look at that now. So it's bounced effectively at the point where it would have crossed the x-axis. And let's just read this here, because I think it's important to just think about this. If we're taking the modulus outside the function, it's going to affect the y value. This is what y is equal to, isn't it? So we've taken our y values always going to be positive if the y is equal to some modulus function. So we're never going to have a y coordinate. If the modulus is outside the function, it's going to be affecting the y values. Just like in our transformations, when we are transforming something outside the function, that's also going to affect the y value. Alright. No, you have to make sure that you show where the y-intercept it has moved to. In this case, it's reflected from negative 3 to 3 as one of those key points in your sketches. Now you might think that the sketch of y is equal to the function of the modulus of x would look the same as this, knowing that the modulus of something must always be positive. But think more carefully and perhaps pause this video for a few seconds to think about what you actually think this would look like. Well, what it's going to look like is a function where effectively both axes are for positive x values. Okay, so if we consider what's going to change for this function when x is positive, it's going to be nothing is going to change when x is positive, because taking the modulus of x will not affect the value of x. When x is 3 here, for example, then it's going to have the same value, and it's going to have the same value when f is, say, when f is 1 here. So we are still going to get a negative y coordinate for this point. However, as soon as we get to a negative value of x, so for example this negative 1 here, This point here for this new function y is equal to the function of the modulus of x is actually going to give us the same y value as if we were trying to calculate this for the modulus of a function of 1, the function of y equaling the function of the modulus of negative 1 is going to be equal to y equaling the function of positive 1. So this negative 1 will become positive 1 when substituted into this or transformed by that modulus. What does that mean? It can go to the negative, but there's still going to be a reflection, but that reflection is now going to be in the y-axis. So this nicely summarizes the first two key points for today's lesson. If you take the modulus of a whole function, it cannot become negative, and it's going to bounce in the x-axis, it's going to reflect in the x-axis, so that it never has a negative value. However, if you take the modulus within the function, that's always going to mean that the input is positive, so there's going to be a reflection instead of the x-axis in the y-axis. Okay, you may want to pause and just read what I've said there in different words down at the bottom here. So let's test our understanding on this. Here's a 2012 question for paper, from a call for paper. Figure 2 shows part of the curve with equation y is equal to a function of x, and the curve passes through these points P and Q as shown. On separate diagrams, sketch the curve with equation y is equal to the modulus of the function of x, and y is equal to the function of the modulus of x. Right, thinking about this, taking the modulus of the entire function would mean that the entire function can never become negative. So we can consider this function here and consider the negative point, which is actually only this section here. So this section here is going to be reflected in the x-axis. Try and replicate when you're doing a sketches the same rough shape. We can see it's going down and with an increasing positive gradient if you're heading in that direction. So it's going to be following the same pattern there, and that's what we're going to get. Now if we're taking if we're now going to sketch the function of the modulus of x, then this graph's shape is going to be replicated for the positive x quadrant, and so we're going to get a reflection from this first quadrant into this quadrant here. We're going to reflect the right hand side effectively in the y-axis, and that's the reason why we're actually going to get a function that looks like this. How about another question? So sketch for within the domain of x, negative 2 pi to positive 2 pi, y is equal to the modulus of sine of x. Pause this video and have a go at these two questions now, please. Okay, let's see how you did. So what's not a bad idea with all of these problems is to just start off with a sketch ignoring the modulus, because that will make it easier to think what has changed. So you should have started off by just sketching what you believe y equals sine x would look like within this domain. So your sine starts at 0, 0, and we're going to get that classic sinusoidal curve, which would do something like this. However, as we've taken the modulus of the whole function, the negative component of this graph is going to be reflected in the x-axis, and we end up with this sort of bouncing effect. So well done if you got the same answer there. Apologies that there's actually a mistake here I've noticed on the x-axis, that these should be in terms of pi, not in terms of degrees. So hopefully your answer is more correct than my answer. Part B, sketching y is equal to sine of the modulus of x. Again, pause if you've not done this yet and have a go. Otherwise, click play and we'll have a look at the answer to this one. So again, we should have started off by sketching, at least in the positive quadrant, what our function is going to look like, and then taking the function of the modulus of x means that that input can never be negative, and so we're going to get a reflection in the y-axis, which means our function looks like this. What I'd like to do now is have a go at some questions that test your understanding further on this. You've got the questions and you've also got the answers, and I'd like you to have to go at question 1, 3, 5, 7, 9 and 10 for exercise 2E, please. Once you've done those and you've checked your answers, click play again, and we'll carry on and look at combining functions too. So when we were looking at combining transformations, we can just quickly reflect and think about what happens when we change the inside of a function and when we change the outside of a function. So if we are changing the inside, so the input of a function, which axis is affected, pause the video now and just have a think about what you would put in these 4 squares, even just saying out loud. Okay, so changing the inside of the function is going to change the x-axis. We're changing the input. So would that be what we expect to happen? That tends to be the opposite of what we would expect. If you think about going from f of x to f of 2x, I would say, my instinct would be that would be a transformation where the function is stretched by a factor of 2 horizontally, whereas in fact we find that it's stretched by a factor of a half horizontally. And likewise, if we add f of x to f of x plus 1 inside the brackets, instead of it moving to the right by 1, it would move to the left by 1. When it's outside the function, that thankfully is not quite the case, and it's more likely to be what we expect. So when we're changing the outside, we're affecting the y coordinates, and that is what we expect. So when we add 1 to a function, we move it up by 1 in the y direction. So again, this is nothing new to what we've already been looking at, and it's just a recap really on what comes next. Here's a graph of y equals f of x. Sketch the graph of y equals 2f of x plus 2. Well, the 2f of x is going to, the 2 outside this function is going to affect the y coordinate, so this is going to mean that it is stretched by a factor of 2 vertically with y, so I know that this a coordinate of -1 will be stretched to -2. And this by coordinate of 4 will be stretched to a value of 8 by a factor of 2. I also know that x plus 2 element of this will mean that instead of it moving to the right by 2, it's going to do the opposite of perhaps what I would expect, and everything's happening 2 earlier, so it's actually going to move left by 2. A, as a result, is going to end up on the y-axis, and B is going to also translate by 2 to be the points, have an x-coordinate of 4. So combining that with our vertical stretch as well, we're going to get this function here. It doesn't hurt to have a dotted sketch of the original function to help you with when you're doing these. And whenever in an exam, say, you're given some key points like these 2, a and b, you have to stipulate where those have been transformed to. So make sure you make it clear. In fact, the one thing missing from this new sketch is just showing the new points a and b, which we would call a dash and b dash, typically. Key is, yes, as said in this box here, start off like was done in the explanation here by considering the key points that you know. There was one extra key point here, and that was 0, 0. And of course we know that that's going to be stretched vertically by a factor of 2, but of course a y coordinate multiplied by 2, if that y coordinate is 0, is going to remain as 0. But we do know that it's going to be intersecting the x-axis 2 to the left of that now, so we actually know that this coordinate as well we could state is -2. So make sure any key point you include. How about these two examples here? You might want to pause and have a quick think about and go at these before you click play. Here is a graph of y equals f of x. Sketch the graph of y equals -f of 2x. Well, again, there's two things going on here. Firstly, we've got a negative of the function, which is going to make a reflection in the x-axis. So we know our b will reflect in the x-axis to become 6, -4, and our a will reflect to become 2, +1. We also know, though, that we've got 2x inside the function, and so all points are going to be stretched horizontally by a factor of a half. So the x-coordinate of b is going to transform to 3, and the x-coordinate of a is going to transform to 1. So if we have a look at what that would look like, we're going to get this. Oops, sorry. Now if we have a look at the modulus of f of negative x, what should we do first here? Work from the inside of the function out. So start by considering what would f of negative x look like, which of course is going to be all the x coordinates changed to the negative of an x. So this will become, as a result, a reflection in the x in the y-axis. It's going to become a reflection of the y-axis as the x inputs have all been swapped around. So my b is going to go from 6,4 to negative 6,4, and my a is going to go from 2,1 to negative 2, negative 1. So the whole function, the entire function, is going to have been reflected in the y-axis. Now then, so when you're doing this question, sketch that first, and then consider what's the modulus of that whole thing going to do. Taking the modulus of that entire function will make everything positive, so everything is going to be above the x-axis. So getting to this final stage is going to be very difficult without taking it in steps and starting off by sketching what f of negative x would be. You would end up with something like, oh, let's get this right. Sorry, yes, so you get something like this. So this section here and this section here has been reflected so that all values are positive. Take your time to have a go at this question, and then we'll be moving on to the final bit of today's lesson, which is a little bit more independent work. So looking at this question, figure 1 shows part of the graph of y equals f of x for any element real in x in our domain. The graph consists of 2 line segments that meet at the point r for negative 3, as shown in figure 1. Sketch on separate diagrams the graphs of f of 2x plus 4 and y equaling the modulus of f of negative x. On each diagram, show the coordinates of the point corresponding to r. Considering the first value, it's going to be translated left by 4. So considering my r has an x coordinate of 4, r is going to move onto the y-axis. And it's also going to be multiplied by 2. So that would mean that the y coordinate of my r has doubled to be negative 6. Aside from that, I'm not given any other key values for this, so I'll just be indicating in my sketch a general stretch here. Having the general shape, so here a general V shape, would get you a mark in an exam, including the key point coordinates of r, also get you the marks, and showing that your vertex is on your y-axis. So effectively the other 2 marks are this off r for having r in the correct point at the correct point. For part B, we're going to start by reflecting the entire function in the y-axis, and then we're going to take the modulus of it so we only have positive values. So by reflecting anything negative in the x-axis, we end up with this W shape. So again, we get a mark for the general shape, 2 vertices on the negative x-axis, W in both quadrant 1 and quadrant 2, and a final mark for the correct coordinates of our new point r dash. What if 2 x changes or 2 y changes? The y values are multiplied by 2 and then 1 is added. That is what happens if we've got 2 of our f of x plus 1. How about if we have 2x plus 1 inside the function though? You will not get multiple x transformations in the exam, but theoretically, if that's the case, the easiest way is to think of the inverse of the function of 2x plus 1, i.e. x minus 1 over 2. This gives us the changes to the x values and in the correct order. In this case, we would negative 1 minus 1 from the x values, which would be a translation 1 left, and then halve the x values, which is a stretch on the x-axis of scale factor a half. This is, just to sort of repeat what's said, this is something that will not happen in your exam, but just so, despite your curiosity, if you are curious, you might want to have a think about this question here, pause and have a go. And doing that, we would get this answer here. Okay, so the final bit of today's lesson is exercise 2F, questions 1, 3 and 5. Thank you.